All right, let's just dive right in. We are going to peel back every single layer of abstraction you know in programming. We're going to find the fundamental, simple truth of what a computer actually is. And you might be shocked to learn that the blueprint for, well, every device you own is actually almost a century old.
I want you to think about it for a second. Every variable you've declared, every complex algorithm you've ever designed, literally every single line of code you have ever written, it all boils down to one and only one incredibly simple action.
That's it, seriously. At its absolute core, that's all that is ever happening. Just a constant, ridiculously fast manipulation of data in memory. And here's the crazy part. This simple, powerful idea existed long before computers were even a thing.
So who's the genius who figured this out? His name was Alan Turing, and he did it in 1936 as a 23-year-old student. He wasn't in a lab full of electronics. He was armed with nothing but a thought experiment, an idea that would literally lay the groundwork for all of modern computing.
See, this was the question that obsessed mathematicians back in the 1930s. Was it possible for any problem to be solved just by following a mechanical set of steps? Turing's answer wasn't some physical machine, but an idea of the absolute simplest possible device that could perform any computation you could imagine.
He called it an automatic machine. Pretty straightforward. Today, though, we call it a Turing machine. And what is just so mind-blowing is how elegantly simple it is. So let's break it down.
That's the number 3. That's all it takes. This universal computing machine, the ancestor of your smartphone, of every supercomputer on the planet, has only 3 core components. Just 3.
Okay, first you've got the tape. Just picture an infinitely long strip of paper divided up into little boxes or cells. Second, you have the head. It just sits over one of those cells at a time and can do only 3 things: read what's in the cell, write something new in it, or move one cell to the left or right. And third, the rules. This is just a simple little instruction book, a cheat sheet, that tells the head what to do based on whatever it reads. That is the entire machine.
And this is the crucial point of this whole thing. Every single computing device you use, your laptop, your phone, the massive servers in the cloud, is fundamentally a Turing machine. It just has a much, much larger tape, a much faster head, and a way more complex set of rules.
So how does this abstract idea from 1936 connect directly to the code that you and I write today? Well, this is where it gets really, really interesting for us as programmers. Let's actually build that bridge right now.
Okay, so let's make that first connection. You see that infinite tape on the left? That is your computer's memory. It's your RAM. And every single little cell on that tape corresponds directly to a memory address in your machine.
Now, the connection gets even clearer when you actually write code. When you type out a simple line like int x equals 5, what you're literally doing is telling the machine's head, hey, go find a specific cell and write the symbol 5 into it. Your variable, x, is just a friendly name we've given to that cell's address. Oh, but it goes deeper. When your code does something like x equals x plus 1, it's just mirroring the Turing machine's fundamental loop. The head moves to the cell, it reads the value, the rules tell it to compute something new, and then it writes that new value right back. That simple read, compute, write cycle, that is all your CPU is ever doing, just billions of times a second.
But the head doesn't just read and write, right? It moves. And that movement, that directly translates to your program's flow. Think about it. An if statement is just the head deciding, based on a rule, whether to move left or right on the tape to find its very next instruction.
Every for loop you write is just the head methodically scanning across a section of the tape. A function call? That's the head jumping to a completely different area of the tape to execute some other instructions and then jumping right back when it's done. And a pointer, like in a language like C? Well, that's literally an address telling the head exactly which cell to go to next. But here's the twist. Here's the insight that Turing himself discovered that changed absolutely everything. Those rules, that instruction book for the head, it doesn't have to be separate. The rules themselves can be written on the tape.
And that single insight gave birth to what we call the stored program computer, which is the architecture of every single modern device. It's the whole reason you can download an app. The app is just data, a bunch of symbols written on the tape, until the computer's head starts reading that data and treating it as instructions. Code is data. So, let's bring this all together. When you're sitting there writing code, it might help to think of yourself not just as a programmer, but as the one actually giving directions to that little head on the tape.
So the next time you write let name equals Alan, just remember, you're just putting a friendly, human-readable label on a single cell on that massive tape. And when you update that variable to Turing, you are commanding the head to go right back to that same cell and just write something new over it.
Every single if-else statement in your code is just a decision point. It's a rule that's telling the head which direction to travel next along the tape.
When you allocate a new object, or maybe a big array, you're simply claiming a fresh, blank section of that seemingly infinite tape, all for your own use.
You know, this even explains our most common errors. Ever gotten a null pointer exception? What does that even mean? Well, it's just the head trying to read from a cell on the tape that's forbidden, or maybe one that doesn't even exist. It really is that simple.
All our high-level languages, our frameworks, our garbage collectors, they are all these magnificent, powerful layers of abstraction. They exist to make our jobs easier, so we don't have to think about moving a head across a tape one cell at a time.
But no matter how complex our code gets, no matter how many layers of abstraction we build on top, what's happening underneath never, ever changes. It's still the same simple, elegant machine that Alan Turing imagined with just a pencil and paper almost a century ago. So the next time you write a line of code, remember what you're really doing. You're giving instructions to a head moving along a tape, reading and writing symbols. You're still using a Turing machine.